So I want you to imagine launching thousands of pounds of heavy server racks on rockets.
Right, straight into low Earth orbit.
Yeah, exactly. And not for satellite communications or, anything we usually associate with space, but literally just because the vacuum of space is a highly efficient way to keep microchips from melting.
Which honestly sounds completely like a concept from a science fiction novel.
It really does. But between March 29th and April 4th, 2026, that actually became a documented infrastructure strategy.
Yeah.
And it really shows that we are looking at a computing landscape that has completely, totally inverted its own rules.
We really have. I mean, we've spent the last few years operating under this assumption that progress in AI simply meant, brute forcing larger data centers on Earth.
Right, just building bigger buildings.
Exactly. We measured advancement by physical mass. But the announcements from NVIDIA this week, they reveal a massive pivot.
A pivot away from just raw power, right?
Yeah. Yeah, the industry is no longer just chasing raw centralized training power. The entire architecture is shifting toward highly efficient, decentralized, and autonomous deployment.
And that right there is the mission for our deep dive today. We want to welcome you to this breakdown where we're basically cutting through the sheer noise of NVIDIA's massive week.
There was a lot of it.
So much. But we want to extract the core metrics and the strategic chess moves that actually matter to you, the listener, if you're trying to stay ahead of the curve.
Because to understand why data centers are heading into orbit or, how frontier-class AI is suddenly squeezing onto the device sitting on your desk, we first have to look at the raw math.
Right.
Performance benchmarks published this week prove that software optimization is moving just as fast as the silicon.
And I think the clearest example of that landed right on April 1st, right?
Yeah.
With the MLPerf record.
Yeah, exactly. ML Commons released their MLPerf Inference version 6.0 records, and NVIDIA's Blackwell Ultra GPUs just delivered the highest throughput across all the newly added benchmarks. Yeah, they set a massive 288 GPU scale record, and that was via their Quantum X800 InfiniBand networking.
But there's a specific metric in there that really caught my eye. It's the efficiency gain on the DeepSeek R1 server throughput.
It's a 2.77 times speed up.
Exactly. Using the exact same hardware they had 6 months ago, they achieved nearly a 3 times speed up. That drops the estimated operating cost to just 30 cents per million tokens.
Which is a cost reduction of over 60%.
Right. And it's basically like realizing your car can suddenly drive 3 times faster.
Yeah.
Just by updating the engine control software. It's insane.
It is. And the way they achieved it is fascinating. They heavily co-designed the hardware and the software using techniques like kernel fusion.
Kernel fusion. How does that actually work in practice?
Well, think of it like reorganizing a commercial kitchen. Instead of the GPU acting like a chef who walks to the pantry for every single ingredient one by one, you fuse the operations together.
Oh, I see.
So the GPU performs multiple mathematical steps while the data is already in its hands. You haven't made the chip physically faster, you've just eliminated the latency of fetching data.
And that's how they racked up their 291st cumulative MLPerf win. Just incredible software routing.
Right. But, throughput is only one side of the coin here.
What do you mean?
Well, the processor's speed doesn't really matter if it has nowhere to store the context of what it's actually working on. And this became glaringly apparent in the April 3rd research published by NVIDIA.
Oh, right. The text-to-JSON benchmark and the whole KV cache offloading paper.
Exactly. To understand the stakes of that research, we have to look at how these models remember things during a task.
The KV cache.
Yeah, the key value cache. It's essentially the AI's short-term memory of a conversation. As context windows have grown to, millions of tokens, storing that memory has become the primary bottleneck.
Not the compute power, but the memory itself.
Yeah, memory is the true bottleneck now. Historically, the industry relied on this thing called heuristic memory offloading.
Because high-speed GPU memory is just incredibly expensive, right?
Exactly, and it's physically limited. So the software tries to guess which parts of a conversation are no longer relevant, and it just dumps them into cheaper, slower system RAM.
It's basically making an educated guess about what the AI can safely forget.
Right. But the text-to-JSON benchmark proves that those educated guesses are fundamentally flawed when you get to complex tasks.
Because the researchers basically introduced this highly complex test where the model has to extract deeply structured JSON data from massive text prompts.
Yeah, and if you ask an AI to pull highly specific data structures out of a million-word document, it really can't afford to forget the schema that was defined on page 1.
Right. If the heuristic offloading dumps that critical context, The AI just completely loses the plot.
It hallucinates or it breaks the formatting completely. The research highlights that you just cannot software hack your way out of the memory wall anymore.
It necessitates actual hardware-accelerated context memory.
Exactly, and NVIDIA is leveraging this benchmark to validate their new CMX platform, basically proving that future workloads require specialized silicon just to manage that short-term memory.
Well, and if the memory wall is the biggest barrier for massive cloud models, it's an absolute roadblock for running AI on local devices.
Oh, absolutely.
Which brings us to that wild April 4th demonstration at GTC 2026, the neural texture compression, or NTC.
That was huge. They figured out how to compress visual texture memory footprints by up to 85%.
85%. That's a massive reduction in VRAM usage.
It is, and the mechanism behind it is a complete departure from traditional rendering. Normally, a 3D texture is stored as an array of texels, which are basically pixels for 3D objects.
So every single point of color and light is saved in memory.
Right, but NTC discards that entirely. It uses machine learning to compress those textures into highly compact, latent representations.
It's like storing the genetic code of an oak tree instead of trying to save a high-res photograph of every single leaf.
That's a perfect way to put it. The GPU's neural cores take that tiny mathematical formula and just reconstruct the visual data in real time when you look at it.
And by shrinking that VRAM usage by 85%, you can suddenly fit vastly more complex 3D scenes or even massive AI inference models locally on standard consumer GPUs.
Which fundamentally alters the deployment landscape. I mean, if you can compress the memory footprint that aggressively, frontier AI no longer requires a connection to a remote cloud server.
Which is exactly the technological foundation that allowed Google and NVIDIA to drop the Gemma 4 open-weight models on April 2nd.
Right. They released day zero optimized versions of these models, ranging from 2 billion all the way up to 31 billion parameters.
And they're built for immediate deployment across RTX PCs, the DGX Spark, and Jetson Edge devices. We are talking about offline AI agents capable of reasoning and coding locally.
Yeah, high throughput, low latency, and totally offline. And they're leveraging NVFP4 quantization to do it.
Right, basically reducing the precision of the mathematical weights down to a 4-bit floating point format. So the models run incredibly fast on local tensor cores.
And without a catastrophic loss in reasoning capability, they actually outpace cloud alternatives in sheer latency just because there is zero network delay.
But deploying highly capable autonomous agents directly onto your local operating system, I mean, that introduces some profound vulnerabilities, doesn't it?
Oh, definitely. If an AI agent has the autonomy to read your local files or write executable code, traditional security perimeters are entirely inadequate.
Which explains NVIDIA pushing the integration of the NemoClaw framework. They're calling it the agent computer.
Right, where the hardware and software are co-designed to sandbox the AI. NemoClaw creates this isolated environment.
So the AI can manipulate local files, but it's bounded by immutable rules. It can't, exfiltrate your personal data to the cloud.
Exactly. It brings the power of agentic AI to the edge while completely neutralizing those privacy risks.
And that ability to securely simulate and manipulate environments locally, that extends directly into robotics too, right?
It does. On April 3rd, NVIDIA released the public documentation for Omniverse NeurAC, which stands for Neural Reconstruction.
This directly addresses the whole sim-to-real gap.
Yeah.
Because if I'm trying to train an autonomous factory robot, I obviously can't have it learn by physically bumping into real walls and breaking expensive equipment.
No, you have to train it in a simulation. But if the physics in that simulation, like the friction of the floor or the mass of an object, aren't perfectly accurate,
then the robot's training is useless in the real world.
Exactly. So NeurAC utilizes standard video and kinematics to mathematically derive and generate fully interactive, physically accurate 3D scenes.
It outputs sim-ready assets, like XODR maps for autonomous driving and USDA files for 3D environments.
Right. It allows engineers to film a physical environment and instantly convert it into a flawless, mathematically perfect physics playground for training AI.
It entirely removes the manual labor of coding simulations.
It's a huge time saver.
And while NeurAC is eliminating the manual labor of coding 3D worlds, NVIDIA also showed off how they're eliminating the friction of coding for GPUs altogether.
Oh, you're talking about the April Fool's post.
Yes. On April 1st, the NVIDIA developer blog posted Qtile Basic. It looked like a joke, but it's a fully functional compiler that lets developers write a 512 by 512 matrix multiply for modern GPUs using the ancient BASIC programming language.
I mean, as a PR stunt, it is highly entertaining.
I was laughing so hard at the idea of using BASIC for cutting-edge AI. But does this actually matter for modern developers?
It actually does. The underlying engineering is profoundly significant. Historically, leveraging GPU acceleration required deep expertise in really complex languages like C++ or specific Python libraries.
Right, you had to speak the GPU-specific dialect.
Exactly. But the fact that this basic code compiles and runs flawlessly, it proves that the new CUDA tile intermediate representation layer is entirely language agnostic.
The IR layer, right. The translation layer between human-readable code and the machine's native binary.
Right. By proving they can target the GPU with a language as rudimentary as BASIC, NVIDIA is demonstrating that their hardware is now accessible to incredibly diverse software ecosystems.
So basically, any developer using almost any language front-end will soon be able to write highly optimized AI compute kernels.
Yeah, they are fundamentally democratizing access to the silicon.
Wow. But, democratizing the software and pushing AI to local edge devices doesn't really eliminate the foundational problem.
Which is the power grid.
Exactly. Training these models in the first place requires infrastructure on a scale that is literally straining the Earth's resources. We are talking about gigawatts of power.
Yeah, a massive data center is traditionally just a static, relentless drain on the grid. It draws a flat baseload of electricity 24 hours a day.
Which clashes terribly with the variable generation of renewable energy, like wind and solar.
The power grid is genuinely the ultimate bottleneck for global AI scaling right now, and that's the context for the March 31st announcement from NVIDIA and Emerald AI.
The Vera Rubin DSX blueprint.
Right. They introduced a system designed to treat AI factories not as static loads, but as dispatchable, power-flexible grid assets.
The mechanism here flips the traditional model entirely. Instead of demanding a constant supply of power, the Vera Rubin blueprint dynamically throttles the compute load based on local grid conditions.
Exactly. So if the grid is stressed during a heat wave, the AI factory instantly suspends its training workloads and sheds its power draw.
It acts like a virtual power plant.
Yeah, and then when solar generation spikes at noon and electricity is abundant, the factory ramps its processing back up to maximum capacity.
And they project this dynamic approach could unlock up to 100 gigawatts of U.S. grid capacity. It basically allows AI data centers to support, rather than strain, the energy infrastructure.
Without requiring decades of new baseload power plant construction.
But if you want to bypass the terrestrial power grid entirely, you arrive at the most staggering piece of reporting this week.
The orbital data centers.
Yes. On March 29th, details emerged on the Space One Vera Rubin module, a specialized hardware unit designed to place high-density AI compute clusters into low Earth orbit.
LEO. Yeah, the physics and the economics of this present a highly compelling case when you look at the constraints of terrestrial infrastructure.
Okay, wait, I have to stop you there. Data centers in space.
Yes.
I have to challenge the logistical reality of this. We are talking about securing payload space on rockets, blasting fragile silicon through extreme acoustic vibration, just to avoid building better solar farms on Earth.
It sounds wild, I know.
The cost of rocket fuel versus the cost of water cooling seems profoundly misaligned.
It does seem misaligned until you factor in the physical limits of high-density compute. On Earth, the single largest operating expense for an AI data center isn't the electricity, it's the cooling.
Right, the millions of gallons of water.
Exactly. And we are approaching a thermal wall where terrestrial liquid cooling systems simply cannot remove heat fast enough from these densely packed clusters.
And space solves that.
Yes. In low Earth orbit, you are exposed to a limitless, natural cryogenic heat sink. You radiate the thermal load directly into the vacuum of space.
Wow.
Plus, a satellite in a sun-synchronous orbit experiences nearly 100% solar availability. There's no weather interference and no night cycle to disrupt power generation.
Okay, so they are entirely decoupling the AI infrastructure from Earth's geographic constraints. That is insane.
It really is.
Well, while the orbital data centers target the macro-scale limits of physics, our next update targets the micro-scale limits of time.
The STAT-ML Tokconomics benchmarks.
Yeah, on April 2nd, audited benchmarks revealed that the GH200 Grace Hopper superchip achieved a 4.61 microsecond P99 latency for LSTM neural network inference.
And just to contextualize that metric, a microsecond is 1/millionth of a second.
Right.
Achieving sub-5 microsecond latency breaks the final barrier for utilizing GPUs in algorithmic trading.
Because historically, if a financial institution wanted to deploy an ultra-low latency trading algorithm, They couldn't use a GPU, right?
Yeah.
They had to rely on custom FPGAs.
Exactly. Field programmable gate arrays. An FPGA is essentially a blank slate of silicon where engineers physically hard code the logic pathways into the chip itself.
Which makes it incredibly fast, because there's no software overhead. But it's notoriously difficult and expensive to program.
Right, and GPUs were always viewed as too slow because executing software commands across thousands of cores inherently introduces microscopic delays.
But this GH200 architecture eliminates that bottleneck.
Yeah, by matching the latency of a custom-built FPGA, NVIDIA allows the financial sector to finally abandon specialized, hard-coded hardware.
They can just deploy standardized GPUs to execute high-frequency trades. That opens up a massive enterprise market.
A highly lucrative one, previously completely walled off to them.
But, when you have AI systems executing financial trades in millionths of a second and autonomous agents writing code on local devices, the conversation inevitably collides with physical safety and global governance.
The stakes transition from software bugs to real-world kinetic consequences.
Exactly. Which is exactly why NVIDIA released the Halos Autonomous Vehicle Safety System on April 4th.
And to be clear, this is not simply a sensor package for a car. It is a unified, full-stack safety architecture.
It provides deterministic guardrails at design time, deployment time, and validation time, from the cloud all the way to the car.
And the scale of the validation here is just staggering. The Halo system conducts 2 million end-to-end integration tests daily.
2 million a day.
Yeah, spanning from the cloud simulation environments down to the physical hardware in the vehicle, it mathematically bounds the neural networks.
So it ensures that regardless of what the AI attempts to learn or execute, its actions are strictly confined by verifiable safety protocols.
Right, before the vehicle ever interacts with a public road, that level of verifiable safety is the absolute prerequisite for widespread regulatory approval.
But the regulatory landscape is fracturing rapidly, especially when you look at the macroeconomic data released by Reuters on April 1st.
Yeah, looking strictly at the market dynamics in the China AI accelerator sector, the real-world impact of U.S. export controls is highly quantifiable now.
The data indicates that in 2025, Chinese domestic GPU manufacturers captured nearly 41% of their local AI accelerator market.
With Huawei alone claiming roughly 20% of that.
Right. And prior to the export controls, NVIDIA maintained an estimated 95% market share in the region, and that is now contracted down to 55%.
It perfectly illustrates the mechanics of market adaptation. Just as a purely factual observation, when access to frontier technology is restricted, the performance gap acts as an intense catalyst for domestic alternatives.
The data points to a rapid acceleration in local silicon development to replace the restricted imports.
Which fundamentally shifts the dependency structures of the global hardware supply chain.
Exactly. And navigating that exact geopolitical shift requires NVIDIA to insulate its global position.
Right, because if the raw compute chips themselves are increasingly subject to regional competition, the strategic imperative is to lock in the foundational infrastructure that connects those chips.
Which brings us to the March 31st announcement. NVIDIA announced a $2 billion investment and strategic partnership with Marvell Technology.
They're integrating Marvell's custom XPUs and advanced silicon photonics directly into the NVLink Fusion ecosystem.
And NVLink has traditionally been NVIDIA's highly guarded proprietary interconnect fabric, right? It's the microscopic highway system for their GPUs.
Exactly. It allows them to share data at unprecedented bandwidth. And the decision to open that proprietary fabric to third-party custom silicon is a brilliant defensive maneuver.
Because the major cloud providers, the hyperscalers, they're aggressively developing their own custom AI processors.
Right. They want to reduce their financial reliance on NVIDIA's hardware. They want to build their own engines.
So by opening NVLink Fusion, NVIDIA acknowledges that reality, but dictates the terms.
They are establishing NVLink as the mandatory interconnect standard. If a cloud provider builds their own compute chip, they still need those chips to communicate at extreme speeds.
So regardless of whose silicon is actually performing the math, the data has to travel across NVIDIA's proprietary toll road.
Exactly. They capture the foundational infrastructure layer of all future AI factories.
They own the grid, regardless of what appliances are plugged into it.
Precisely.
And that level of architectural dominance is reflected in the final major milestone of the week. On April 4th, driven by sustained global demand, NVIDIA achieved a historic $4 trillion market valuation.
First company globally to reach it. And this milestone cements a concept analysts are calling Tokenomics.
Tokenomics. Explain that framework for us.
Well, we're entering a phase where the AI token, the fundamental unit of processing a word or an image, functions as the primary unit of enterprise productivity.
Oh, I see.
In a tokenomics system, a company's competitive advantage is entirely dictated by its ability to generate and process tokens faster and more efficiently than its rivals.
And by controlling over 80% of the AI processing market, NVIDIA has basically positioned itself as the central bank of this new economy.
They are the architect of it. They are dictating the foundational cost of intelligence for the global market.
We have covered an immense architectural pivot today. I mean, in the span of a single week, between March 29 and April 4, 2026, we saw software optimizations drop inference costs by 60%.
We saw frontier models compressed down to run autonomously on local edge devices.
Protected by hardware-level sandboxes, we analyzed the transition of AI factories into dispatchable grid assets and the actual logistical realities of launching data centers into the vacuum of low Earth orbit.
From replacing FPGAs and high-frequency trading to securing autonomous vehicles.
And locking down the global interconnect standards. The landscape has fundamentally shifted.
It is the definitive transition from simply accumulating raw compute power to the highly efficient, ubiquitous deployment of intelligence across every layer of infrastructure.
Absolutely. Well, thank you for joining us on this deep dive. But before you go, considering this reality of tokenomics, I want to leave you with a final thought to explore on your own.
It's an important one.
We've seen the infrastructure required to mint these AI tokens scale from local desktops all the way to orbital satellites. But as this tokenized intelligence becomes the undeniable baseline for global economic productivity, what happens to the enterprises or even the developing nations that just can't afford to build their own AI factories?
Right.
Are we rapidly accelerating toward a future where cognitive capability itself is metered, distributed, and sold exactly like electricity?
It is the geopolitical question that will define the rest of the decade.
Something to carefully consider. Until next time, keep diving deep.